Ever just stop and think about what your computer is doing right at this very moment? I mean, you've probably got a bunch of tabs open, maybe some music streaming, notifications popping up. It's this constant high-speed juggling act. And the fact that it all just works? That's kind of a small miracle. So let's pull back the curtain and see how it actually pulls it off.
So yeah, that's the big question, isn't it? How can all these different programs run at the same time using the same brain, the same memory, without just collapsing into a pile of digital chaos? Well, the answer lies with the true unsung hero of your device, the operating system. Okay, to really get a handle on this, let's use an analogy. I want you to picture your computer's operating system, the OS, as the super smart, unflappable manager of a crazy busy restaurant. Now, in this restaurant, every program you're running, say your web browser or your music player, is a talented but, let's say, single-minded chef. They all need to use the main kitchen stove, which is your computer's CPU. And every so often, they all need to use the exact same special ingredients, which are just shared bits of data in memory. The manager's one big job? Make sure none of these chefs burn the kitchen down.
So, what's the very first problem our manager has to deal with? It's what happens when two chefs try to grab the very same ingredient at the exact same time. It is a classic kitchen nightmare, and in the world of computer science, it has a very specific name. It's called a race condition. This is what happens when the final result of something totally depends on the unpredictable sequence of events. Just imagine two programs in a dead sprint, a race, to change the same piece of information. Whoever gets there last is the one who determines the final value. And that final value is very often wrong. And here is the perfect real-world example of why this is so bad. Think about two separate bank transfers trying to deposit money into your account at the exact same microsecond. Both of them read your starting balance. Let's say it's $100. They both add their deposit. But because they're in a race, one transfer's final result might just completely overwrite the other one. You could literally end up with less money than you were supposed to get, all because of bad timing. That's a race condition. So how does our OS manager stop this from happening?
Well, the manager's first and most important rule is simple, it's direct, and it is absolutely non-negotiable. It's really the golden rule for sharing things safely, and it's called mutual exclusion.
Mutual exclusion means pretty much exactly what it sounds like. If one process is using a shared resource, all other processes must be excluded. It's our restaurant manager laying down the law. Only one chef can use the special salt shaker at a time. No exceptions. This simple rule prevents two chefs from grabbing it at once and making a mess. And this little diagram shows you exactly where that rule applies. You see, the specific part of a program's code that actually touches that shared resource, our special ingredient, is called the critical section. Our OS manager puts a sort of digital velvet rope around this section of code. And if you want to get in, you have to ask for permission first.
So the whole process becomes nice and orderly. Step 1. The program, our chef, asks the OS for permission to enter that roped-off critical section. Step 2. If nobody's in there, the OS says, go ahead and grants access. Step 3. The chef gets to work with the ingredients totally safe from anyone else interfering. And then, Step 4, and this is the really important part, the chef leaves and tells the OS, hey, I'm all done. They release their access so the next chef who's been waiting in line can get their turn.
Now, this one-at-a-time rule is a great start, for sure, but it's also a little basic. What happens if the kitchen has more complex needs? Well, for that, our OS manager has a much more sophisticated tool they can use.
It's called a semaphore, and you can think of it like this. It's a single key that opens the pantry where all the special ingredients are kept. If a chef needs an ingredient, they have to physically grab the key. Now, if another chef comes along and sees the key is gone, well, they just have to wait. Simple as that. There's only one key, so only one chef can be in the pantry at a time.
In programming terms, the OS uses two really simple commands to manage this whole key situation. The first one is wait. That basically just means wait for the semaphore, or in our analogy, wait for the key to be available. Once the program has the key, it can enter its critical section and do its work. When it's finished, it uses the second command, signal. This just means I'm releasing the key. It's hanging it back on the hook so the next program in line can grab it and go. It's simple, it's elegant, and it's incredibly effective.
But here's the twist. The very rules that we just created to bring order to the chaos can, under just the wrong set of circumstances, create a brand new and maybe even more frustrating kind of problem, a complete and total standstill.
This problem is called a deadlock. It is, for all intents and purposes, a digital traffic jam. Imagine you have two programs. Program A has a resource that Program B needs to continue. But at the same time, Program B has a resource that Program A needs. Neither one is willing to give up what it has, so neither one can move forward. They are permanently stuck waiting for each other in this infinite loop of nothing.
The classic example that shows this perfectly is known as the dining philosopher's problem, but let's just call it the stuck chefs. Picture 5 chefs sitting around a big table with a bowl of spaghetti in the middle. Now, between each pair of chefs, there's a single chopstick. To eat, a chef needs 2 chopsticks, the one on their left and the one on their right. So what happens if every single chef picks up the chopstick on their left at the exact same time? Well, now, every chef has 1 chopstick and is waiting for the one on their right, which is being held by their neighbor. Nobody can eat, nobody can put their chopstick down, they are in a deadlock.
So it turns out, for this kind of digital gridlock to happen, 4 very specific things have to be true at once. First, mutual exclusion. Only one chef can use a chopstick at a time. Second, hold and wait. Each chef is holding 1 chopstick while waiting for another. Third, no preemption. You can't just snatch a chopstick out of another chef's hand. And finally, circular wait. Chef 1 is waiting for Chef 2, who's waiting for Chef 3, and so on, all the way around the table back to Chef 1. The cool part is, if you can just break one of these 4 conditions, you can prevent deadlock from ever happening.
And that brings us right back to our restaurant manager, the real star of this whole operation. Because preventing those race conditions and breaking potential deadlocks before they can even start, well, that's the OS's full-time job.
Just think about that for a second. Every time you click, every key you press, every background update, each one is a potential race condition or a potential deadlock. And your OS is just constantly, tirelessly analyzing all the requests, managing all the little keys, and running these incredibly smart algorithms to make sure that those circular waits never form and that everybody gets a fair turn. And it does this millions of times every single second.
So what all this really means is that the smooth, stable experience you have on your phone or your computer is absolutely not an accident. It's the result of decades of brilliant computer science, all of it just humming along silently in the background. It's your own personal, invisible restaurant manager, making sure all the chefs play nicely so you can enjoy your digital meal in peace.